Okay, talking about now partial pressures and Dalton's law. So our cells continuously use oxygen and produce carbon dioxide. That's cellular metabolism. Both gases moving in and out of the lungs through the membranes of the alveoli, which are the tiny air sacs at the ends of the airways in the lungs. So what we're going to do is use Dalton's law of partial pressures to calculate the total pressure of gas mixtures. Okay, so let's look at this. So a partial pressure of a gas is the pressure that each gas in a mixture would exert if they were by themselves in the container. So we have helium and argon here, and we can see that when they're combined, we can have a combined ATM of 6. When the helium was 2, argon was 4, 2 plus 4 equals 6. So we are going to now learn how to calculate partial pressure. So Dalton's law of partial pressure indicates that the pressure depends on the total number of gas particles, not on the types of the particles. So the total pressure that's exerted by gases in a mixture is going to be the sum of the partial pressures of those gases. So PT, which is total, is going to equal P1 plus P2 plus P3, infinity. Okay? So for an example, at STP, okay, which would the 1 mole of pure gas in a volume of 22.4 liters will exert the same pressure as 1 mole of gas mixture in 22.4 liters. All right, so here you can see 1 mole of nitrogen is 1 atmosphere, where again you have 0.4 moles of oxygen plus 0.6 moles of helium, and that would give you 1 mole, and that would exert 1 mole of ATM. Again, 0.5 plus 0.3 plus 0.2 is 1 mole, and that's 1 mole. So regardless of what the mixture, we're still going to end up having the same pressure. Okay. So the air we breathe is a mixture of different gases. And this contains mostly nitrogen and oxygen and small amounts of other gases that you can see in this table. What we call the atmospheric pressure is actually the sum of the partial pressures of the gases in the air. So our handy-dandy little guide for solving partial pressures is going to be step 1, write the equation for the sum of partial pressures. Step 2, rearrange the equation to solve for the unknown pressure. Step 3, substitute the known pressures into the equation and calculate the unknown partial pressure. So let's work one together. So a scuba tank contains oxygen with a pressure of 0.45 atm and helium at 855 millimeters of mercury. What is the total pressure in millimeters of mercury in the tank? Remembering that volume and temperature in this example are going to remain constant. So step 1, let's write the equation for the sum of the partial pressures. So the total is going to be the sum of the oxygen plus the helium. So let's rearrange the equation to solve for the unknown, convert the units to match, and we end up getting 342 millimeters of mercury. All right, so then scuba tank again contains this. So step 3, we're going to substitute the known pressures and calculate the unknown pressures. Okay, so remember that the P total is PO2 plus PHE. So we have 342 millimeters of mercury plus 855 millimeters of mercury, and that ends up giving us 1.20 times 10 to the 3rd millimeters of mercury. All right, so let's try it yourself. Here's the equation. For a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8 atm, 8.00 atm. If the oxygen has a partial pressure of 1,280 millimeters of mercury, what is the partial pressure of helium? Remembering that volume and temperature are going to be constant. Pause me, do your calculations, and come back. Right, so what we see is that for a deep dive, a scuba diver is going to again use that mixture. So let's write the equation for the sum of the partial pressures. So remember, P total equals PO2 plus PHE. We're going to rearrange the equation to solve for the unknown pressure and convert the units to match. Okay, so we have to have ATM over ATM equals millimeters of mercury. And then we are going to substitute the known pressures and calculate the unknown pressures. Okay, and that ends up giving us that the answer is C, which is 4,800 millimeters of mercury. All right, so how do we apply this? Well, what are blood gases? In the lungs, oxygen enters the blood while CO2 from the blood is released. In the tissues, oxygen enters the cell and that releases carbon dioxide into the blood. So you can see your tissues here with our values: oxygenated blood, deoxygenated blood, our lovely heart, the alveoli where we're doing the oxygen exchange, and our values. So this equates into our blood gases. So in the body, oxygen is going to flow into the tissues because the partial pressure of oxygen is higher in the blood and lower in the tissues, where carbon dioxide flows out of the tissues because the partial pressure of CO2 is higher in the tissues and lower in the blood. So here are our partial pressures of blood and tissues. For the gas, our O2 is here, our oxygenated blood is 100, deoxygenated blood is 40, tissues was going to be 30 or less. Where for CO2 and our oxygenated blood, it's going to be 40, deoxygenated blood is 46, tissue is going to be 50 or greater. So what happens with gas exchange during breathing? Well, our partial pressures of oxygen and carbon dioxide in blood and tissues. So you can see again here a handy dandy little chart to summarize that. So our overall gas concept chart, flow chart, is going to be here, where we have gases are described by kinetic molecular theory of gases, and it states that the gas particles are far apart, they move fast, and they exert pressure. They're going to behave according to gas laws that relate to pressure and volume. That's going to be Boyle's law. Volume and temperature, that's Charles' law. Pressure and temperature, and that's Gay-Lussac's law. Combining them all together would be the combined gas laws, where the volume and moles are related to V and N using Avogadro's number, where at STP it gives us the molar volume. So for a gas, it's going to be the gas mixture, where the gases are going to exert partial pressures, and they're used to find the moles or volumes of gases in the reaction gases. Great job, guys.